Okay, so let's have an example on this. Let's have, or let f of x equal to the exponential function e to the power x, and the Fourier coefficients of f, let's assume that already we have obtained them on this interval. This is minus L and this is L, are, so we are, do you remember that we want to obtain a node, an, and bn? Do you remember that? So these are the values, or these are the integrals that we're going to obtain. Using them, we're going to obtain the Fourier series. Okay, so these are the coefficients of equation 13.1 as far as I remember. Okay, if you don't know about this, please revisit the previous videos. So you have the integration in order to obtain a node from minus L to L, from minus 1 to 1, the function dx. Okay, this is easy. You can obtain it as e minus e to the power minus 1. And an, it is going to equal from minus 1 to 1 the function itself time cosine n pi x over L, right? L here is equal to what? Exactly, L equal to 1. So already it's not written here. So it's n pi x over L, or over 1 dx. Now this is integration by parts and it is easy to be obtained, and you can obtain it like this. Remember that we said cosine n pi x, or cosine n pi, we can put it by minus 1 to the power n, if you remember. Okay, so now we have, this is the terms related to the coefficient an in the Fourier series. Let's go to the bn, the coefficient of bn. It is going to be the same function, the integration of course from minus L to L, the same function times sine n pi x dx. So we're going to find that it gives us this fraction here, and we are going to find that at the end the Fourier series of the function e to the power x on the interval minus 1 to 1 is going to be like this. This is half a node, because we have a node here, and then this is a constant outside of the summation from n equal to 1 to infinity, with this value here, as you can see it here, minus 1 to the power n over the denominator times cosine n pi x minus n pi sine n pi x. Okay? Okay, now because e to the power x is continuous with a continuous derivative for Lx, that's right, because this is continuous without a doubt. Ex is a continuous function. There is no jump here, right? This series converges to, without thinking too much, converges to e to the power x, which means that it is within the limit between minus 1 and 1. The function, the Fourier series here, is going to converge to what? Without thinking too much, e to the power x. It is the function itself. Okay, and what about the limits, minus 1 and 1? How we are going to think about them? Yes, exactly. It is going to, based on the application of the theorem, half of the function, okay, from both left and right. So e to the power 1 plus e to the power minus 1. Okay, for what? For the limit, which is x equal 1, and for the other limit, which is x equal to minus 1. Without thinking, from where we got this? Please go back to what we have mentioned before. Exactly. So at minus L and L, the function is going to be half of f of L from the left plus f of minus L from the right. Okay, this is at the interval limits. Okay, I hope that you got the meaning and the point of this. Let's draw it to understand more about this. Now, this is the 13th partial sum, means that 13 terms we have used them to get the Fourier series. So as you can see here, between minus 1 and 1, the Fourier series function, almost it is very close to the function. Okay, so it is going to exactly converge to the function itself, which is e to x. However, at the ends, which is minus 1 and at 1, we're going to find Fourier series converges to what? Look to this line here, and comes here, and then here, and comes here. Converges to what? Exactly, is this value. Do you know what is this value? it is half times e plus e raised to minus 1. So it equals to 1.54, okay, which is this value. Okay, so this is at the end here. We are talking about the limits here. They are at the ends. Okay. Okay, so we have this this example. So we have this function, as you can see it here. This function equals to, take care of the limits here. We have 5 sine x for x larger than or equal to minus 2 pi and less than minus pi over 2. So we start here as if that we are talking about the minus L here, okay, and f of x is taking different values, and we are going to end with exactly with L here. So this is like the limits, okay, minus L and L here, and in between the function is taking different values. Okay, so we can find that at specific values like 4, for example, the function takes a specific value. So at x, the function equals to 4 when x, the independent variable, equals to minus pi over 2, and it equals to x squared over the interval. This is the interval, okay, and then it equals to 8 cosine x for this interval. Take care, we have this limit 2 is going to be, that is between, like the pivot between the two jumps here, and then we have 4x for x between pi and 2 pi. This is the interval here, okay, because remember, well, the main value is, or the main Fourier series function converges to f of x, okay, in whatever we are between minus L to L interval, and it equals to half, okay, the f of L when we are talking about L from the left, plus f of minus L if we're talking about minus L from the right. Okay, so this is half of it at the limits. This is at the limits. Okay, I hope that we remember this well. Okay, now let's go and try to think about it. First of all, if you look to the function itself, you're going to find all the function, all the values of the function that it assumes. It is all of them, they are piecewise and smooth. Okay, not only continuous, but they are smooth. What is the significance of this? Exactly, let's go back. Okay, I already done it, but we said that if it is piecewise and smooth, then the convergence of Fourier series, yes, f of x, whenever that we are in between the limits minus L and L, and half of f of minus L plus L from the right, sorry, from the left, no, sorry, this is from the right, and then it is going to be f of L from the left, something like this. Okay, so these are the two main assumptions that we are going to use for the solution. Okay, as long as it is piecewise smooth from minus 2 pi to 2 pi. The Fourier series of f on this interval converges to, first of all, this is 5 sine x, and we have this interval. So this is, yes, piecewise smooth, right? Because the derivative also is piecewise continuous. So we have 5 sine x, which means f of x of the function. So Fourier series converges to 5 sine x in this interval too. But we found that there is minus pi over 2 here, minus pi over 2 here, and then there is minus pi over 2 here, and in between minus pi over 2 is taking a value from the function. So as if there is a jump here, there is a jump, right? And we need to take care of minus pi over 2. So at x equal to minus pi over 2, our function is going to be what? Exactly. We are going to have two values here. From, let's assume from the left and this is from the right. So we're going to have this value. It is going to be half x squared, okay, fx squared plus 5 sine x, right? So we are like having f as fx from the right and f of x from the left, right? So they are going to be summed up and we multiply by 1/2. So x squared, it is going to be pi over 2 minus pi over 2, because we are talking about x here, okay, x as if that it is minus pi over 2 because we are talking at this particular point at the jump. And 5 sine x, actually sine x is going to be sine pi minus pi over 2. We are talking about minus pi over 2 always. So it is minus pi over 2, right? So it is going to be minus 1 times 5. It is going to be minus 5. So we put it here. So this would be Fourier series at this point is going to be half times pi squared over 4, pi squared over 4 minus 5, as we said, and sine minus pi over 2, it is going to be giving us minus 1, so it is already here. Okay, now let's go to the interval, the next interval. This is interval, okay, piecewise smooth, so it is going to be x squared, the same function. So x squared is going to be the convergence of Fourier series for this limit. But here in between we have also 2 and we have 2. So we need to stop at the 2 at this value and see what is the convergence of Fourier series at this value. So we are going to stop at 2 for x equal to, and then we are going to look from the left and from the right. So we are going to again from the left and from the right. Before it was x squared and after it is 8 cosine x, right? X squared and 8 cosine x. So it's very easy. We're going to have half, and before it was, we are talking about x equal to. So this means that x squared equal to 4. So this is x squared equal to 4. So this is 4 here. And then 8 cosine x, which is going to be 8 cosine 2. Okay, so we are having the function from the left and from the right, and we are halving them. Okay, and then 8 cosine x, it is an interval from 2 to pi, then it is going to be the same 8 cosine x as it is the same. Then at pi we're going to find that it is repeated here and it is jump here, so we need to stop at pi. At pi we need to stop here as I indicated, and then we're going to find that what is before and what is after. Before 8 cosine x, after is 4x. So we're going to have two values here, okay, the same fashion also. So we have half outside and from the left and from the right. So we are having 4 pi, which is 4x, I mean, because we are talking about x equal to pi, and 8 cosine pi. So it is going to be minus 8, right? Okay, and then let's go to the last interval, which is 4x. This 4x is going to equal to what? The convergence is going to be the same function, which is 4x, because it's an interval. And then at the end we have 2 pi, okay? And at the end we have 2 pi. Actually, we need to think about 2 pi and minus 2 pi. Do you remember that I said this is minus L and L, right? So this means that at 4 pi, sorry, at the ends, which is at x equal to 2 pi and x equal to minus 2 pi, which is at L and minus L, the function converges to what? Exactly 4 pi. From where I got it? Yes, half times f of L from the left plus f of minus L from the right. It equals to half 5 sine x, 5 sine x. Do you remember? This is 5 sine x plus 4x. Okay? It is vice versa, actually. It should be vice versa, because I think this is minus 2 pi, and larger than minus 2 pi, it is going to be 5 sine x. So this is as if we are approaching from the right. Okay, so this is from the right for minus L, so this is 5 sine x, and this is if L minus, which is from the left, it is going to be, yes, for this 4x. Okay, so anyway, if you are going to sum them up and multiply by 1/2, you are going to find sine x, in this case sine 2 pi, or sine minus 2 pi is going to be, sorry, this is sine minus 2 pi, it is going to be 0, right? And then the last thing is 4 times x, which is 4 times 2 times pi, and then this 2 cancels with the half outside, it gives us 4 pi. Okay, so it is going to converge to 4 pi here. Okay, I hope that you have understood this example. It is, even that it takes a little bit time, but it is very straightforward and simple, and always apply the two rules that already I have explained to you before. So the first rule is related to at the interval ends, it is going to be half times f of L from the left plus f of minus L from the right. And if we are talking about inside the interval, then we are going to talk about the same function f of x. If our function is piecewise, this is the prerequisite. Okay, this is the condition for us. Otherwise, it will be very easy for us to continue. Okay, thank you, and see you in the next video.